Let us now take a look at the calculation rules for complex numbers. First, investigate the addition and subtraction. For everything that follows, assume that we have two complex numbers, w, which is a plus bi, and z, which is x plus yi. Then the addition and the subtraction are very easy. If you have w plus z, this is just a plus x plus I times b plus y. W minus z is a minus x plus I times b minus y. So you just add or subtract the real parts to each other, and you add or subtract the imaginary parts to each other. The addition or the subtraction is commutative, so we have commutativity, which means that it doesn't matter in which order I perform the subtraction or the addition. So if I have w plus z, this is the same as z plus w. Also, associativity holds for complex addition and subtraction, which means that it doesn't matter where you put the brackets in the addition. So if we have z1 plus z2 plus z3, so we have three complex numbers, then it doesn't matter if I do first the addition of the first two and I add the third one last, or I start with adding the last two and I add the first one. So it doesn't matter in which order I perform my addition or my subtraction. And then also there is triangle inequality. This means that the modulus of a sum or a subtraction, so z plus w or z minus w, can never be larger than the sum of the moduli separately. So this is smaller or equal than z modulus plus the modulus of w. The triangle inequality is very clear once you plot the different parts in the Argand diagram. So let's start by plotting the diagram, so plotting the complex plane, and place 2 points z and w inside this complex plane. Next, construct the sum z plus w and also the difference z minus w. To construct the sum, we complete the parallelogram of z and w. So it means that we close the parallelogram with sides z and side w. The diagonal of that figure is then the sum z plus w. To do the same thing for z minus w, we first indicate minus w. Minus w is just the opposite across the origin, so we make a mirror image across the origin of w. This is minus w, and then we do the same thing. We complete the parallelogram between z and minus w to find the subtraction z minus w. If we then look at the plot, we see that the modulus of the sum is the length of the red line, and the modulus of the difference is the length of the yellow line. From geometry, it is known that the diagonal is always smaller than the sum of the two sides in a triangle. So we see it as a triangle with a side w, a side z, and then a side z minus w or a side z plus w. And so for any triangle to be a triangle, the length of one of the sides can never be larger than the sum of the other sides, otherwise you cannot form a triangle. So this shows visually that the modulus of the sum or the modulus of a difference is always smaller than the sum of the moduli of z and w. And then also there is the final property for subtraction. We have that w plus z, and we take the conjugate, so we take the conjugate of a sum is just the sum of the conjugates. The proof of this is extremely simple. We just write it out. So we have on the left hand side, we have w plus z conjugate. So w was a plus bi, we add z was x plus yi, and now we take the conjugate of this total sum. So we will reorder the different terms. So a sum of complex numbers was a sum of the real parts. So this is a plus x plus I times the sum of the complex or the imaginary parts. So b plus y, and then the conjugate of this thing. We know that the conjugate just changes the imaginary part of sine, so this becomes a plus x minus I times b plus y. And then we reorder again. This is a minus bi plus x minus yi. So this is the conjugate of w plus the conjugate of z, which is what we needed to prove. Let's then take a look at the product of two complex numbers. So again, we have w, which is a plus bi, z is x plus yi. So then the product wz is very easily calculable, and it gives you that it is ax minus by plus I times bx plus ay. The proof is very straightforward. So w times z, you replace w and z by their expression. So this is a plus bi times x plus yi. And then you just work out the product like this. So this is a times x plus a times y times I plus bxi. And then we have also a term by I squared. The real part is then the ax plus by I squared. I squared is minus 1, so this becomes minus by. And then the imaginary part is ay plus bx. And this is just the formula we have. Furthermore, if you multiply a complex number with its conjugate, this product is the modulus of the complex number squared. The calculation for this one is even more straightforward than the previous one. So z was x plus yi times the conjugate x minus yi. This is just a special product, so it is x squared minus yi squared. Yi squared is I squared minus 1 times y squared, so this is x squared plus y squared, which is the modulus of z squared, because the modulus of z is the root of x squared plus y squared. Furthermore, the product is also commutative. So if I do z times w or w times z, it doesn't matter. It is associative. So the order of the multiplication doesn't matter. And finally, we also have distributivity. So this means that if I have the multiplication of a sum, so I have z1 times z2 plus z3, this is just z1 times z2 plus z1 times z3. And then also, if we have a multiplication, we take the conjugate. So the conjugate of a multiplication is just the multiplication of the conjugates. To show this, we just write down the different parts and work them out. So z was x plus yi times a plus bi, and we take the conjugate. We then apply the rule for the multiplication. So this is ax minus by plus I times bx plus ay, and the conjugate of this. Then we know that the conjugate changes the sign of the imaginary part. So this is ax minus by minus I times bx plus ay. Then it is possible to verify that this is the same as x minus yi times a minus bi, which is z conjugate times w conjugate. We can also consider the product in polar form. Recall that in polar form, a complex number is represented by the modulus and the angle. So assume we have two complex numbers, w, which is r times cosine of theta plus I sine of theta, and z, which is s times cosine of phi plus I sine of phi. So we know then that the modulus of w is equal to r. The argument of w is the angle theta, and the same for z. The modulus of z is s. The argument of z is the angle phi. We can then calculate the multiplication w times z. So w times z is r cosine theta plus I sine theta times s cosine phi plus I sine phi. We take out r and s easily, r times s. And then for the rest we can see this as some a plus ib, as some c plus id, and we will just use the multiplication rule for complex numbers. This multiplication then becomes cosine theta times cosine phi minus sine theta times sine of phi plus I times sine theta cosine phi plus cosine theta sine of phi. Then we use trigonometry to see that cosine theta cosine phi minus sine theta sine phi is just cosine of theta plus phi. And the other one here, sine theta cosine phi plus cosine theta sine phi, this is equal to sine of theta plus phi. What we then see is that the modulus of w times z is r times s. So it's just the modulus of w times the modulus of z. And for the argument of wz, the angle in the complex number, in this case is theta plus phi, which is the argument of w plus the argument of z. What we thus see in polar form is that the modulus of the product is the product of the moduli, so we just multiply those with each other, and the argument, so the angle in the complex number for the product, is just the sum of the separate angles. So it's the sum of the angle corresponding to w plus the sum of the angle corresponding to z. And this property also holds more generally. So if we have a multiplication of n different complex numbers, so we have z1 times z2 up to zn, then the modulus of this product is just the product of all the separate moduli, and the argument of the product is the sum of the different arguments. So it's argument z1 plus the argument of z2 and so on up till the end. A very important theorem for complex numbers, or for a product of complex numbers, is de Moivre's theorem. For this theorem, take a complex number z equal to cosine theta plus I sine of theta. So here we have the specific case that the modulus is 1, and then the argument of z is the angle theta. We then apply the previous theorem, so z to the power n is actually z times z times z, so n times. So what we see is that the modulus of z to the power n is the modulus of z times the modulus of z and so on n times. So it is the modulus of z to the power n because of the property that we saw on top of this slide. And in this specific case, the modulus is 1, so it's 1 to the power n or equal to 1. And then for the argument, so the argument of z to the power n is according to the second line of this slide. It is the argument of z plus, again, the argument of z plus, and then finally again plus the argument of z. So we have here n times the argument of z, or n times theta. So de Moivre's theorem tells us that if I have cosine theta plus I times sine of theta, and I take the nth power of this, this is just cosine of n times theta plus I times the sine of n times theta. So here, if we have a complex number with modulus 1, we take this to the power n. What happens is that we multiply the arguments by n, so we have n theta instead of theta. The only thing that then remains is to define the division of two complex numbers. So how do we divide two complex numbers, for example z divided by w? The way to do this is by multiplying with the conjugate in the denominator. So what we do is this is z over w times w conjugate over w conjugate. We then plug it in, so it is x plus yi times a minus bi over a squared plus b squared. Or this is equal to x times a plus y times b plus I times y times a minus x times b divided by a squared plus b squared. It's then possible to look at the modulus and the argument of the division. So the modulus of z over w is the modulus of z over the modulus of w, and the argument of z over w is the argument of z minus the argument of w. For the conjugate, we have the following properties. First, we already saw that the conjugate of a sum is the sum of the conjugates. We saw the same thing for the multiplication. So if we multiply z and w, we take the conjugate. This is just the multiplication of the conjugate separately. If we take the conjugate of the conjugate, we find the complex number itself, which is very easily to verify. So you have x plus yi. You take a double conjugate. You do the first one, so it's x minus yi. You still have one conjugate to go. Again, the imaginary part changes sign. So this is x plus yi, which is z itself. Fourth property, if we take z to the power n and we take the conjugate of this power, this is the same as the conjugate of z to the power n. Here we just apply the multiplication. So z to the power n conjugate is z to the power n minus 1 times z conjugate. Then the second rule tells me that this is z to n minus 1 conjugate times z conjugate. And then we keep continuing this until we have z conjugate times z conjugate times z conjugate, which is just z conjugate to the power n. And then the fifth property, if a multiplication of two complex numbers is 0, then this means that either z is equal to 0 or w is equal to 0. So if my multiplication gives me 0, one of both numbers has to be 0. As a remark, these properties allow us to easily calculate the conjugate of an expression. So to find the conjugate of an expression, the only thing you have to do is to replace every I by minus I, and that's it. So there is no need to first calculate the expression or to work out the expression. You can just replace every I by minus I and you will get the conjugate of the full expression. For example, you have 5 plus I times 6 minus 3i squared divided by 7 minus 12i. If you want to find the conjugate of this expression, this is very easy. It's 5 minus I, 6 plus 3i to the power 2, and divided by 7 plus 12i. So I just replace every I by minus I, and then if you like, you can verify that this is correct. Let's then look at some examples. So for the first one, calculate 3 plus 5i times 4 minus 2i. Second one, what is the value of I to the power 23? Third one, make the division 3 plus 5i over 1 minus 2i. And then the fourth one, what is 7 plus 3i divided by 4i? So try to solve these examples by using the calculation rules that we saw. The first one is very straightforward. You just multiply both terms. So this is 12 plus 20i minus 6i minus 10i squared. So it's 12 plus 10, it's 22, plus 14i. For I to the power 23, what we do here is we have, this is I times I to the power 22. This is I times I squared to the power 11. Then we have I squared is minus 1 to the power 11 times I. So minus 1 to the power 11 is minus 1. And so this is minus I. So to solve this division, so to find the complex number which is the solution of this division, we said we have to multiply with the conjugate of the denominator. So we multiply both the numerator and the denominator with 1 plus 2i. The numerator then becomes minus 7 plus 11i divided by 1 plus 4, which is 5. And then the final one, we divide 7 plus 3i by 4i. We could multiply by the conjugate, so by minus 4i in the numerator and the denominator. This gives me minus 28i minus 12i squared, so this becomes plus 12 over minus 16i squared, or 16. Then we can divide every term by 4, so this is 3 minus 7i over 4. In this case, we could also have worked a little differently, because we divide by a purely imaginary number. So the denominator is purely imaginary. So what we could have done was 7 plus 3i over 4i is 7 divided by 4i plus 3i over 4i. So the 3i over 4i is very easy, 3 over 4. And then 7 divided by 4i. What we do there is we just multiply everything by I. So it's 7i divided by 4i squared. So we get 3 over 4 minus 7i over 4.